Welcome back, class. So last time we studied about the convolution and the different properties of the LTI system like stability, memoryless, time variant, and the other properties. So now we are going to start the next topic of difference equation representation of the LTI system and the discrete time Fourier transform. So that are the topics which we are going to cover in today's lecture. So basically we have learned that convolution is the one form of the representation of the discrete time system, that you have the input, you have the shifted impulse response, and you multiplied them and take the summation for the all values. So another form of the discrete time system representation is difference equation representation. Okay, so we can represent the discrete time using this equation. Okay, so it's like this. For example, I'm writing an output as x of n plus x of n minus 2 plus x of n minus 3. Okay, so we can write like this one. Okay, or we can write like this one: y of n plus the shifted y of n is equal to this whole, for example. Okay, so this is also a form of the output representation of a discrete time system. So in general, okay, we take the summation of the output multiply with a constant, and we take the summation from 0 to n, and similarly for the input. Okay, the shifted, or like if k is 0, so it will be x of n, like that. So this system is called recursive system. Okay, if the value of the ak does not is equal to 0. Okay, for any value of k greater than 0. Okay, so then our system will be recursive system. Okay, recursive means the system is occurring. Okay, so for example, this example, okay, this example is a recursive system, and this example is a non-recursive system. Okay, non-recursive system, like you only have y of n. So for example here, so y of n is the summation of the x of n only. Okay, so this is called non-recursive system. And for the non-recursive system, for example, this is my input, and we know that if I make the input as impulse, so output will become an impulse response. So impulse response can be represented with h of n when the input will be impulse. Okay, so this is just another representation of the impulse response in the discrete time system. So these are the different examples of the discrete time representation. There are a couple more examples. The one is ideal delay system, that you are delaying the input. Okay, for example, we are just getting x of n minus 2. So this is called delay system, that the input is delayed by 2. So this is also a non-recursive discrete time system. Okay, moving average system. Okay, like you have the shifted impulses, shifted inputs, and you are want to take the average of that. Okay, for example, for this is like this, that this is my input, and I want to take the average of, for example, these fours, and then I want to take the average of these four. So this is called moving average. Okay, so I will add these four. Okay, for example, this one, and so on, and I will divide it by their sum is their total number. Okay, plus 1, and similarly go on. Okay, so this is also an example of the discrete time difference equation representation. And next we have one more example, which is called accumulator system. Okay, so the accumulator system is like you just perform the summation. Okay, for example, let's start x of 0, x of 1, x of 2, and so on. Okay, and like also negative, so just adding all the values. This is also one example. Okay, this is called accumulator system. Okay, the next question is, show that this system can be written as like this one. Okay, we have to show that this system can be represented like this one. Okay, so this we will solve in the live session. So if we have a general difference equation, so the next is how we can actually calculate the solution of the difference equation. So basically the solution of a difference equation constitute of two components: homogeneous solution and particular solution, like a differential equation. Okay, so this final solution will have two components, homogeneous and the particular. And when we want to find the homogeneous solution, we know that we assume the input is equal to 0. So all the input components should be equal to 0. So the general solution of the difference equation in homogeneous form is exponential. Okay, lambda power n. Okay, so whatever difference equation we have, we will replace the y of n with the exponential power, and with respect to that, and then we just do some simplification, and we can get a polynomial equation. Okay, like second order, third order, or higher order polynomial equation, and from that we can find the roots of that polynomial. Okay, so that will give us the generalized solution. Now the roots could be complex, real, or identical. Okay, so if we have real root and not identical, different, for example roots are -3 and -4, so these are real roots and they are not identical, so the general solution will be this one. Okay, a constant multiplied by that root power n, constant multiplied by second root that power n, and so on. And if the roots are identical, then that root power n, and then n times that root power n. Okay, so that will be the solution, and so on. Okay, so the last thing is how we can calculate the values of these coefficients. So by using the initial conditions we can find these values. So this is the procedure to get the homogeneous solution. The particular solution is, particular is that if we have some particular input, then what will be the output. So for example, so there are fixed solutions. If the input is a, for example a constant, so the output will be a constant k. If the input a exponential m power n, so output will be k times m power n. Okay, a is just replaced with the m. If the input is impulse, particular solution will be 0. If the input is unit response, k times that unit response. Exponential times u of n, k times exponential times u of n. N times u of n, k naught n plus k1 2, or k naught plus k1 n. Okay, so these are the fixed particular solutions. I have just given a couple of examples, but there are a lot of others, but we are going to put focus on only on this. So these are the examples that for the difference equation find the solution. So we will solve the examples in the live sessions. The last thing is discrete time Fourier transform. Okay, so we have learned in the continuous time system that we can take the Fourier transform of the system, okay, by integrating the input multiplied with the exponential signal. Okay, like if we have x of t a to the power minus j omega t. Okay, so if we integrate, we will get the Fourier transform of that system, right? So in discrete time, what is happening? As we learned earlier, we will replace the integral with the summation sign, input multiply with e to the power minus j omega n. Okay. Discrete time exponential signal. Okay, so this is called analysis formula. So like if we have x of n, if I take its discrete time Fourier transform, I will get x e to the power j omega. Okay, this is called pair, discrete time Fourier transform pair. Okay, and if I have x of j of omega and I want to get x of n, so I will just integrate. Okay, for the one period 2 pi multiply power e to the power j omega n with respect to d omega. Okay, so this is just the basic definition of the discrete time Fourier transform. Okay, sometimes x of e of j omega is called the Fourier transform, and also it is called spectrum of x of n. Okay, what is the spectrum of x of n, and usually it converges when the system is stable. Okay, stable means if this summation of the amplitude of the input signal is less than infinity. Okay, that is actually the basic definition of the stability. So this is the main formula that if you have any signal, if you want to calculate its discrete time Fourier transform, we can calculate using this. Again, example that if you have unit impulse response, unit step signal, then how we can calculate this discrete time Fourier transform. We will solve this in live session. Impulse signal, how we can calculate this discrete time Fourier transform. Rectangular, again. So these are the examples which we will solve in the live session. So the last thing which I quickly want to tell you about the filters. Okay, so basically for any filter we can get Fourier transform, and the Fourier transform, the magnitude of the Fourier transform can tell us give us information about the characteristics of that particular filter. For example, if you look at this filter, so this filter is basically a low pass filter, that only low frequency signals within this range that will be passed and all other will be rejected or stopped. Okay, so this is an example of a high pass filter. Okay, so only this high frequency, this is high pass filter, only high frequencies will be passed and low frequencies will be stopped. So because this is 0. Okay, and this is a band pass filter, band pass filter, that only these frequency bands will be passed and these will zeros, this will be stopped. This is called band this is called band stop filter, that only these frequencies will be stopped, and this is called band pass. These frequencies will be passed and all rest will be stopped. Okay, so from the plot of the frequency response of the filters we can determine the characteristics of the filter. Fourier transform properties, theorems like for the continuous time, like linearity, like if we have a shifted, okay, so in the frequency domain it will be multiplied with the e to the power minus j omega nt with that signal Fourier transform. If we are multiplying with e to the power j omega in time domain, okay, discrete time domain, in frequency domain we will have the shift. Okay, so similarly, like the convolution in time domain is the multiplication of the Fourier transform in frequency domain. So these are all the properties, okay, like the continuous time. So table will be given, you don't have to memorize, but you should understand that how you apply the properties like in the continuous time system. General Fourier transform pairs, like if you have an impulse, its Fourier transform will be 1. If you have shifted impulse, its Fourier transform will be this. If you have unit step, if you have exponential signal, and like that. Okay, so these are the general table. So by using this table we can solve the different equation. Examples which we will solve in the live session inshallah. Thank you very much class for your time. That's the end of today's lecture.